So let's now go over signed representation. So signed integers. So we were talking earlier about how n bits can represent 2 to the n things, so why not just split it into half positive and half negative values? I mean, the first logical step that I can think of is to make it so that the sign is another bit. So this actually brings us to our first representation called sign and magnitude. So we basically treat the most significant bit, or the first bit, as the sign. I've put on this slide an example of 3 bits, what values we would actually be able to represent. So let's now go through it. So if I want to represent 0, all I would want is all zeros, or a 1 in the sign's place, and zeros. So we have 2 zeros. We have a positive 0 and a negative 0. That's not the most ideal, but it is a thing that sign and magnitude has. How about the most positive value? Well, in this case, we want to put the sign bit as 0 because we want it to be positive, and all the other bits, which are the magnitude bits in reality, to be all 1s. So that would give us the largest possible number, which would be 2 to the n minus 1 minus 1. How about the most negative number? Well, similarly to the most positive number, we want to have all the magnitude bits as 1, but now we want to have the sign bit also as 1, so then we're saying that this is negative. So that would give us negative 2 to the n minus 1 minus 1. How about incrementing these values? Well, incrementing positive values, that works, but if we add 1 to like 3 in our example when we have 3 bits, that kind of gets weird. Also, if we try to add 2 negative numbers, we actually just make it so that it is a smaller value instead of the larger negative value for what it should be. So this is not quite ideal. So another representation we have is bias notation. The basic idea here is we will take a range of bits, treat it as an unsigned value, and then add some bias to this. Do note that you'll see different documentation. Sometimes you add the bias, sometimes you subtract the bias, and sometimes the bias is positive or negative. You basically need to read on whatever the source is to see if they're adding it or subtracting the bias. I tend to like to add the bias and then have a negative bias if I want to represent negative values. So a conventional bias, if we want to represent negative values, is 2 to the n minus 1 minus 1. And so this will give us, if we use that conventional bias for these 3 bits, this will give us the range as you can see on the slide over there. So how do we represent 0 with this? Well, in our case, with this given bias, 0 is 0 on as the most significant bit and all 1s. How about the most negative number? Well, once again, the most negative number is very similar to unsigned, where it's the smallest unsigned value, which is just all zeros, which means the most negative value we can represent is our bias, which is negative 2 to the n minus 1 minus 1. How about the most positive number? Well, the most positive number is also similar to unsigned, which means it's going to be all bits on, which means we can represent values up to 2 to the n minus 1 with our given bias. How about incrementing? I mean, incrementing is kind of like unsigned, though there are some issues where technically you're adding the bias twice into the number, which is not what you want. So it's kind of a pro. We'll call it a pro. Other pros is the most positive and negative values are the smallest and largest possible representation in unsigned. But a pretty big con is that 0 is no longer all zeros. I mean, 0 is a very common value that you'll see in programming, so that's not necessarily the best thing. So there's another representation we can use, and that's called 1's complement. So the idea is that we'll generate negative numbers from the positive values by just flipping or complementing the bits. This means that we'll be turning a 0 into a 1 or a 1 into a 0. I have once again put on this slide the different values that we would get with 1's complement if I had just 3 bits to represent it. So now let's go through and see what are the largest possible values and zeros we actually have. So 0 in our case here is just all zeros or all 1s. Once again, we have 2 zeros, which is, we don't really like that much. But the most negative number? Well, the most negative number in our case is going to be a 1 in the most significant place and zeros otherwise. So this would represent, or this value is negative 2 to the n minus 1 minus 1. How about the most positive number? Well, the most positive number is going to be all 1s except for the most significant bits place, which is going to be 0, which means that it's going to have a value of 2 to the n minus 1 minus 1. How about incrementing 1's complement? Well, it's kind of like unsigned, except for there's like a really weird edge case where if the most significant bit overflows or has a carryout, we're actually going to wrap that around and add that to the beginning of the number. So it's kind of really complicated, to be honest. So we don't really like that. So that's a pretty big downside for 1's complement. After all, computers are doing a lot of addition, subtraction, and arithmetic operations. So we want those to be as simple as possible. So there's another representation called 2's complement, which takes the idea of 1's complement where we complement or negate the bits, but then it adds a twist. The twist specifically is a 1. So in this case, if we want to get a negative value, we can just take the positive value, negate the bits, and then add 1. So in reality, what this is saying is that the most significant bit is going to represent a negative value of whatever that bit is. For example, here, we can see that this value here that I have my mouse over is 2 to the 4, but it's now negative, so that's negative 2 to the 4. Or 2 to the 2, sorry. So that will give us negative 4. Similar for negative 3, this is still negative 4, but now we have a positive 1 here, because all the other bits are positive here, which means we'll get negative 3. You can see the similar thing for 2, because this is a 2, and this is negative 4, so negative 4 plus 2 is negative 2, and so on. And for the positive values, we don't need to worry about it, because this most significant bit is 0, and all the other bits are positive. So that's the big idea with 2's complement. So how do we represent a 0 in 2's complement? Well, it's really nice. A 0 is just all zeros. How about the most negative number? Well, this is a little bit more complicated. It's slightly different than like unsigned, but we're going to just make it so that the most significant bit is a 1 while all the other bits are 0. So the most negative number is going to be negative 2 to the n minus 1. How about the most positive value? Well, the most positive number is going to be all 1s except for the most significant bits place, because once again, that's the only bit that is negative. So in this case, we're going to be able to represent values up to 2 to the n minus 1 minus 1. How about incrementing? Well, incrementing is just like unsigned, which is a really great benefit. Also, something to notice is that we can now use the sign bit, or the most significant bit, as a sign bit, so we can quickly determine if a number is positive or negative. So some other reasons why we use 2's complement is it is used by all modern hardware. It's nice because it's roughly evenly split between the positive and negative values, though we do have one more negative value because we claim that we have a positive 0. So that's a benefit, kind of. We can also use the most significant bit as the sign bit, which is also really nice. Say you want to quickly tell it, is this number positive, is this number negative? 2's complement makes it super easy. How about negation? Well, negation is also fairly simple. We just flip the bits and add 1. As you can see, if we had 7, which is all zeros except for 3 1s at the end, we just flip all these bits, so this is just all 1s here, like you can see here, 0, 0, 0, so it would be all zeros, but then we add 1 at the end, so this is negative 7. So conversion is very, very simple with 2's complement. So now, let's talk about, let's review what we just learned about 2's complement. So suppose we had 5 bits, what range of integers can we actually represent in 2's complement? I want you to think to yourself, what different representations would actually represent each of these values? Because these all could be represented with some of the different representations that we just discussed. I'll give you about a second or so, though I'm probably going to be impatient to skip on slides, so you should probably pause the video and think to yourself which representation each of these numbers is. Okay, I'm bored. So let's go over the first one. So negative 31 to 31, well, if we want to do this, well, we'd need 6 bits, so that doesn't even matter. How about negative 15 to positive 15? Well, with 5 bits, we could represent that, but we need to use 1's complement. How about 0 to 31? Once again, we could represent that with 5 bits, but we need to use unsigned, so we couldn't use that. How about negative 16 to positive 15? Well, we could use 5 bits to represent that, and actually we could use 2's complement to represent that. How about negative 32 to positive 31? Similar to A, we'd need 6 bits, which means the correct answer in this case was D. Give yourself a pat on the back if you got that correct. So for the next lecture, the next lecture video, we will talk about how we deal with overflow in computers.